Welcome everyone to our Advanced Data Science course here at Platzi. My name is Will Wolf. I'm a data scientist most recently at a startup in New York City. And today we're going to walk through a brief example of predicting footballer ratings by fitting some simple machine learning models. To begin our example, we'll open up our Jupyter notebook and import data about European football players. I had downloaded a dataset in the form of a SQLite database from kaggle.com/datasets with metadata for over 10,000 European footballers. For each footballer, we have the overall rating as attributed by experts to this footballer, and our goal in this analysis is to predict what that rating is. The idea with this prediction, the idea with many machine learning models, is to automate this process of rating these players. Of course, these expert human raters are expensive, and so with machine learning, the idea is to take data about previous ratings, build a model, and make those predictions on future players. And so the first thing we'll do is import our dataset. It comes in the form of a SQLite database, and we'll run a select all statement against the player stats table in that database and create a pandas data frame. So we'll examine this data frame. We see we have two unique identifiers, player FIFA API ID and player API ID, and on a variety of dates, statistics taken about each player. So overall rating is the column we're trying to predict, and we have many other columns on which to make this prediction. And so our first goal is to actually clean this data, to scrub this data. It did appear that before, for each player, we had data taken on multiple dates. So let's corroborate this quickly. So it does look like for each unique combination of player API ID and FIFA API ID, we do have multiple observations for each of these columns. For this one 14, this one 21, etc. So the first thing we'll do is just take the most recent date on which that player was given stats for each player. We'll group by those two unique identifiers, player API ID and player FIFA API ID, our composite key, and apply that Boolean mask to our data frame. The next thing we'll do is select a few columns we care about. Of course, there are many columns in our data frame, and we can take a look at what they are right now. Each one most likely contributing to that overall rating. Their standing tackle score, their aggression score, their balance score, etc. However, when building machine learning models, we start small. We take a few pieces of data that we think contribute to the result, the thing we're trying to predict, and we go from there. And so to start, we'll select a few columns that we care about, that we think, in fact, will contribute to predicting this overall rating. So overall rating is our Y value. In this regression problem, again, overall rating is a continuous value. And ball control, short passing, finishing, and reactions, we think, as one who knows a bit about football, although really just only a bit, will contribute to that response, the thing we're trying to predict. So we'll select these columns and filter our data frame. Cool, so now we have 5 columns. 4 will be used as X covariates, and our final column, overall rating, as our Y value. The next, of course, and I'll put my header back, is to handle null values. And so we'll take a look at any rows that have null values. We see it's just 2 in this case, and we'll go ahead and drop them. So now we have just over 11,000 rows, or metadata for 11,000 European footballers. And now we can move forward with a clean set of data. So the first thing to do when fitting machine learning models, when building mathematical models, is to visualize our data, to look at it, to see if we can observe any relationships in that data that we hope to capture with mathematical models. And so using very convenient pandas plotting functionality right there on that data frame, we can visualize relationships. So on the diagonal, we have a histogram of the distribution of the values in each column. And off the diagonal, we have XY plots for one covariate versus the other. And so here, overall rating is the thing that we're trying to predict. And so we see that and if we go to the bottom here, we see ball control, short passing, finishing, and reactions. So the relationship between overall rating and ball control In most of the plot is linear. However, overall it's a nonlinear relationship because we can't in fact draw much of a line through this data. The best fit might be here, but of course there isn't really a strong linear trend there. We observe the same thing with short passing as well. Finishing, our trend looks rather non-existent for the most part. And finally, we observe a strong linear relationship between overall rating and reactions. So my personal guess is that reactions will play into this prediction, be one of the most important predictors of overall rating. And so the next thing we'll do is go about fitting different machine learning models. Again, we have several covariates, and we observe that the majority of the relationships were nonlinear. When building machine learning models for a regression problem, the first model we're most likely going to try is linear regression. It is the simplest model. It does assume linear relationships between each of our covariates and our target. However, because it is so simple, we typically use it as a baseline. If the linear regression model ends up being your strongest model, perhaps there's something else at play that needs to be fixed, especially when we do observe nonlinear trends in our data. And so the first thing we'll do is separate our data. We'll pop off our overall rating column and set that as Y, and we'll set our X matrix to player stats. We'll take a look at the top, the first few values. We'll make sure the shape of our X matrix looks okay. We'll scale our data next. When building linear models, the scales of the different covariates do matter. It's typically very problematic if the values for one column are 100, 120, 110, and the values for the other column are 5, 4, 3, 8, 6. So scaling our data is typically an important step when building these linear models. And so the next thing we'll do, of course, is separate our train and validation sets so we can have a simple cross-validation procedure or framework. We'll manually create a Boolean index separating our training tests and our validation set. And so we'll say 70% of our observations should be for training, the other 30% for testing, or rather for validation, to assess the performance of our model before actually predicting on real data on those future footballers. Finally, we'll define an error metric. An error metric is a quantification of how bad it is to be wrong. An error metric tells us that when we make a guess and we're not quite perfect with that guess, how bad that really is. And so for our regression problem, we're going to define a canonical error metric, our root mean squared error, taking the real answer and the thing we predicted, subtracting those two values, taking the mean across the sum of those subtracted values, and finally taking the square root of that sum across all of our rows, across all of our predictions. So we'll define that function here, and finally go about fitting a linear model. We're going to import scikit-learn's linear regression object here. We're going to instantiate that object, fit it with our training data, with our X train and our Y train, finally predict on our validation data, and compute an error metric. And so here we see a root mean squared error of 3.9, which, given that most of these values are around 60, 70, 80, etc., having a root mean squared error of roughly 4, to me, doesn't seem so high. If that value was a lot closer to 20, 30, it would be more of cause for concern. But just to be sure, let's actually inspect the coefficients of our model and see what kinds of relationships we're observing. And so we see that from the outset, the strongest relationship was in fact for reaction, I believe was the column. And of course, we do observe much weaker relationships amongst the other variables as well. However, from the outset, we said two things: that linear regression models for regression tasks are typically the baseline model, the one we expect to perform the weakest, and therefore the one we start with but ultimately try to beat. Almost more importantly, we did observe nonlinear trends in our data, so between our individual covariates and our target, and so fitting a nonlinear model is most likely the way to go. And so a random forest model is probably our first choice, a very popular nonlinear model that finds both nonlinear trends between each individual covariate and our target, and also intrinsically uncovers interaction effects between covariates and our target. And so we'll undergo the same process and compute a root mean squared error. And already we see that we did a bit better. As our final step, we're going to observe our feature importances and see in fact which features contributed most to discerning the value of our target. Similar to before, we see that reactions is the most influential variable in this analysis. This has been a brief example of a typical data science workflow. For more, visit us at platzi.com/datascience.